So we have question 4. It says the diagram below shows a bullet of mass 20 gram that is traveling horizontal. The bullet strikes a stationary 7 kg block and becomes embedded in it as it is shown on the diagram below. The bullet and block together travel on a rough horizontal surface a distance of 2 meters before coming to a stop, right? Then 4.1 says use the work energy theorem. Now you can see with this one was specific in what formula we need to use. It says use the work energy theorem, meaning we are only limited to using this formula. Any other formula, any other energy principles here would be wrong, because this one is saying specifically use the work energy theorem to calculate the magnitude of the velocity of the bullet block system immediately after the bullet strikes the block, given that the frictional force between the block and the surface is 10 newtons. Now, before you can get to solving, you want to draw a free body diagram representing all the forces that are acting there, right? So if, for example, we check this bullet block system, we can see that the forces acting there are obviously the normal force because it's on the surface, and then we have the gravitational force, and then acting in the opposite direction of the displacement is your kinetic frictional force. Then obviously this is our displacement. We can just indicate it there just to see the angles there. Then okay, now we can see that the only force that will be doing work on that block there will be the Fk, right? So Fn and Fg, they're not doing work because, as you can see here, they are perpendicular to the displacement. A force that is perpendicular to the displacement cannot do work on the object. So now, having to apply our formula, W net is equals to change in Ek. Now we understand that the only force that will be doing work there is the kinetic frictional force. So we have that work done by Fk is equals to change in Ek. Now breaking this down, we know that's Fk delta x cos theta, and then here breaking this one down, it's half m, and then we have Vf squared minus Vi squared, right? Then we were told that our frictional force is 10, and then this block travels a displacement or distance of 2, then cos 180 degrees. Then we have half the mass. Now let's solve the one for the mass. Remember, we are looking at the bullet block system. So if this is a bullet block system, that means we must add the masses of this two. Now we are given that the block is 7 kg and the bullet is 20 grams, right? But then remember, we don't want our mass in grams, we want it in kilograms. So we have to divide this one by 1000, and then it gives us 0.02 kg. Now, in order to find the mass of the bullet block system, we obviously have to add these ones. Then they will give us 7.02 kg. Now, this is the mass that will be substituting in here, 7.02. Then what is our V finally? Remember, they said after the bullet is embedded in the block, the bullet block system moves until it comes to a stop. So until it comes to a stop, the word stop means the velocity finally will be 0. Now the V initially is what we are looking for, as we were told here to calculate the velocity, the magnitude of the velocity of the bullet block system immediately after the bullet strikes the block. Now, having to punch all this in your calculator, you have negative 20, and then this here will give you negative 3.51, right? And then that's Vi squared. Now here we divide both sides by negative 3.51 like that. Then our Vi squared will give us 5.698 and all those decimals. So you don't want to round it off, you want to keep it in your calculator and then square root. So you'll just press your square root and press answer, then it will give you that value without having to round off this one, right? Remember, you can only round off in the final answer. So when you are here rounded off, you have 2.39 meters per second, and that's the magnitude of the velocity. Now 4.2 says state the principle of conservation of linear momentum in words free 2 marks. So you just go quickly. Principle of conservation of linear momentum states that in an isolated system, the total linear momentum is conserved. Now 4.3 says calculate the magnitude of the velocity with which the bullet hits the block. Now you can see the hint there. In 4.2 we've been asked to calculate we've been asked to state the principle of conservation of linear momentum, and then in 4.3 they ask us to calculate the magnitude of the velocity. This is a hint in physical sciences that after stating this you would probably need to use that same formula for the principle of conservation of linear momentum in order to calculate what comes up as a follow-up question, right? So always observe the trend. So we have sum of momentum initially is equals to sum of momentum final. Now making use of our formula, we know this is a case whereby we have two objects that were moving separately, and then after contact they move as a unit. So this is how we indicated the formula for that. That's m1 v1. So let's take this one as the bullet, indicate bullet, and then we have m2 v2. So this is for the initial part. Let's take this one as the block, and then is equals to, remember after contact they move as a unit because they said the bullet is embedded in the block, then they will have the same velocity. Now this is bullet block system. What is the mass? The mass of the bullet is 0.02. Then the velocity initially, that's what we are looking for. We are looking for the velocity in which the bullet struck the block. Then 7. Here we are told that the block was stationary. So here strikes a stationary 7 kg block. So if the block was stationary, what was the velocity? It was 0. Then the masses, since now they are a system, 0.02 plus 7, we add them together. But remember, in the previous question, we were calculating the velocity of the bullet block system. So that's 2.39. Now having to calculate here, we have 0.02 VI, and then is equals to, punch all this in your calculator, you have 16.7778. Divide both sides by 0.02 like that, and then VI is equals to, if we divide this one out, we have 838.89. Now you should not be afraid when you see a value this big, especially if we are calculating the velocity of a bullet. The bullet can move in such great speeds, so this is nothing surprising.